When people ask how the universe began, they usually point to the textbook picture of the Big Bang. They imagine an infinitely small, infinitely dense little dot of matter and energy sitting in an empty void, which suddenly explodes outward, creating space and time and galaxies and us. It's a very neat, comforting story. But as a physicist, when I look at the equations of quantum gravity, string theory, and holographic information, I come to a very different, much more unsettling conclusion. The question isn't what sparked that initial explosion. The question is whether the concept of a beginning even makes sense when the fundamental geometry of space-time itself is fluctuating like a boiling pot of water. Today, I want to show you why the laws of physics, specifically quantum mechanics and the bounds of information theory, are screaming at us that our traditional view of the Big Bang is fundamentally, logically, and completely incomplete. Now, look, let's be very precise here. You see, the popular science version of the Big Bang on television, or you read about it in some high school textbook, and it is almost always depicted as a bomb going off in a dark room. It's a very Newtonian way of thinking. You assume the universe is a big empty box, a rigid stage, and all the matter just blew up inside it, rushing outward to fill the empty corners. But the universe is not a box. The Big Bang wasn't an explosion in space, it was an explosion of space. But even that isn't the whole truth. If we rewind the clock of the universe, shrinking everything down, we don't just get a smaller and smaller box, we eventually hit a mathematical wall where the equations that built the modern world just stop working. Let me step over to the chalkboard here. I want you to visualize something we use every day in relativity. Let's write down the core of Einstein's general relativity just to ground ourselves in the reality of the math. G mu nu plus lambda g mu nu equals 8 over pi gc to the power of 4 t mu nu. On the left side, we have the geometry of space and time, how it curves, how it bends. On the right side, we have the matter and energy inside that space. John Wheeler used to say that space tells matter how to move, and matter tells space how to curve. It is a beautiful, elegant dance. When we run this equation backward, we see the universe contracting. The galaxies get closer together, the temperature skyrockets, the density approaches infinity, and if you follow this classical trajectory all the way to t equals 0, you get a singularity. Now, don't get confused by the popular science version of singularities, where they are treated as physical, real objects. You hear people talk about the singularity as if it was a tiny, glowing marble that contained everything. In physics, when we see a singularity in our equations, it doesn't mean we have discovered an infinitely dense point of infinite temperature. It means we have discovered the limit of our own ignorance. It means Albert Einstein's beautiful theory of general relativity just threw its hands up and divided by 0. A singularity is not a physical reality, it is an alarm bell. It tells us that our macroscopic laws of gravity have catastrophically failed because they have collided head-on with the quantum realm. The point is actually quite subtle. General relativity assumes that space and time are perfectly smooth. Think of it like a perfectly ironed bedsheet. No matter how close you look, it remains continuous. But quantum mechanics tells us that the universe is decidedly not smooth. Energy comes in discrete packets, or quanta, and if you look closely enough at space and time, they too must lose their smoothness. Down at the Planck scale, which is roughly 10 to the power of minus 35 meters, the smooth sheet of spacetime becomes a violently churning ocean of quantum probability. Down there, you can't even define the concepts of before or after. time itself loses its arrow. It's a bit of a nuisance for our classical intuition, but the ledger must balance. You cannot use classical smooth equations to describe a purely quantum fluctuating event. So, what actually happened? If the singularity is a mathematical lie, what was the universe doing at its supposed beginning? To understand this, we have to look at the thermodynamic balance sheet of the early universe. And we have to introduce a concept that actively prevents us from seeing our own origins. We call it cosmic inflation. For a long time in the 20th century, physicists thought the Big Bang was just a smooth deceleration from a violently hot start. But there were massive problems with this. For one, the universe is incredibly uniform on large scales. If you look at the cosmic microwave background radiation, the glowing echo of the early universe, it is the same temperature in every direction to 1 part in 100,000. But those different patches of the sky are so far apart that light hasn't had enough time to travel between them since the beginning of the universe. If they have never communicated, if they have never exchanged heat, how did they reach the exact same temperature? It's as if you walked into a massive lecture hall where thousands of strangers were sitting, and every single one of them was holding a cup of coffee that was exactly 85.34 degrees. It defies thermodynamic logic. To solve this, my colleague Alan Guth and others realized that in the very earliest fractions of a second, the universe must have undergone an unimaginably violent exponential expansion. Space didn't just expand, it stretched by a factor of at least 10 to the 26th power in a fraction of a second. Space stretched much, much faster than the speed of light. Now, you might say, wait a minute, the speed of light is the ultimate speed limit, but that only applies to things moving through space. Space itself can do whatever the hell it wants. Inflation solves the temperature problem because before inflation, everything was crammed together, exchanging heat, equalizing its temperature. Then inflation took that tiny uniform patch and blew it up to become our entire observable universe. But inflation does something absolutely terrifying for cosmologists. It is the ultimate cosmic eraser. Imagine the universe before inflation had all sorts of chaotic, interesting structure. Maybe it was bouncing from the collapse of a previous universe. Maybe it was a tangled mess of multidimensional quantum strings. Maybe it had complex geometry. Inflation took whatever that initial primordial state was and stretched it so far, so fast, that it completely flattened it out. If you take a deeply wrinkled balloon and inflate it to the size of a galaxy, the surface is going to look perfectly flat and featureless to anyone standing on it. Inflation wiped the hard drive of the cosmos. The thermal bath of particles that was left behind after inflation stopped, the incredibly hot, dense plasma that eventually cooled into hydrogen and helium, is what we actually call the Big Bang today. We can't see past that wall of fire. The universe is actively hiding its origins from us. To create the smooth, orderly cosmos we live in, the universe had to aggressively delete the quantum information of its own birth. But it gets even more complicated and frankly far more interesting when we ask what drove this inflation. Inflation is driven by something we call vacuum energy. Even in completely empty space, there are fields. Think of a field like the surface of a pond. Usually the pond is flat at its lowest energy state. But the early universe was trapped in what we call a false vacuum. It was like a ball stuck in a small dent on the side of a steep mountain. It wasn't at the true bottom, so it possessed a massive amount of pent-up potential energy. This energy was repulsive. It functioned like an anti-gravity that blew space apart. Now, quantum mechanics tells us that this false vacuum is inherently unstable. Because of quantum tunneling, parts of space can spontaneously drop from the false vacuum down to the true vacuum, releasing all that pent-up energy in the form of hot matter and radiation. This is exactly what happened in our patch of the universe. Our specific pocket of space rolled down the hill, inflation stopped locally, and the energy dumped into our bubble created the hot Big Bang. But here's the chilling part. The equations of eternal inflation suggest that while our little bubble stopped inflating, the space around it didn't. Most of the universe is still expanding exponentially, creating new bubble universes forever. It is an endless fractal of creation. In this picture, our Big Bang is not the beginning of everything. It is just a localized event, a tiny spark in an infinitely larger, eternally expanding, multidimensional block of cheese, where each hole in the cheese is another universe with its own Big Bang. Asking when the universe began in this context is completely missing the larger geometry. It is an incredibly stubborn cosmic cipher, one that refuses to give us a definitive starting line. Let me erase this part of the board because we need to go deeper into the information physics. Let's bring black holes into this, because you cannot understand the origin of the universe without understanding how nature handles information. I spent a good part of my life locked in an intellectual war with Stephen Hawking over this exact concept. Hawking argued that when things fall into a black hole, their quantum information is eventually destroyed when the black hole evaporates. I said that couldn't be true because if information is destroyed, the bedrock of quantum mechanics completely unravels. Eventually, we realized that the information isn't lost. It is stored on the two-dimensional surface of the black hole's event horizon. This is the holographic principle. It states that all the three-dimensional physics playing out inside the region of space can be entirely described by a two-dimensional theory operating on the boundary of that region. It's like a hologram on a credit card that projects a 3D image. If we apply this principle to cosmology, the implications are utterly profound. The equations of string theory, specifically the ADS/CFT correspondence, tell us that the space and time we experience are not fundamental. They are emergent. Just like temperature is not a fundamental property of a single atom, temperature only emerges when you have billions of atoms bouncing off each other. Space and time only emerge from the complex entanglement of quantum information on a lower dimensional boundary. So, what does this mean for the Big Bang? It means that trying to pinpoint t=0 might be a fundamentally flawed endeavor. If time is emergent, then at the extreme energies of the early universe, the very concept of time melts away. The beginning of the universe isn't a point in time that you can just fly back to in a spaceship. It is a boundary condition in the mathematics. Think of it like the center of the Earth. If you start traveling north, you keep going north. You cross the equator, you cross Europe, you hit the Arctic. But once you stand exactly on the North Pole, the concept of going north ceases to exist. Every direction is south. It's not that there is a physical wall there, or that you fall off the edge of the world. It's just that the coordinate system you are using simply terminates. Time works the exact same way. When we push our physics back to the Planck era, the temporal coordinate simply terminates. Let me write this down because it is the most striking piece of mathematics we have regarding the nature of time. When we try to write down the quantum state of the entire universe, we use something called the Wheeler-DeWitt equation. It looks deceptively simple. Here it is the Hamiltonian operator, which represents the total energy of the universe, and the absolute value of psi is the wave function of the entire universe. Now, in standard quantum mechanics, the Schrödinger equation tells us how a wave function evolves over time. But look at this equation. There is no time variable t in it. It equals zero. The total Hamiltonian operator acting on the wave function of the universe tells us that fundamentally the state of the universe does not change. At its deepest, most fundamental quantum level, the universe is timeless. The progression of time, and therefore the very idea of a quote unquote beginning, is an illusion created by our macroscopic perspective. We are observers trapped inside the universe, watching the entropy increase. The second law of thermodynamics dictates that entropy, the measure of disorder, must always increase in a closed system. Because the early universe was in a state of extremely low entropy, it naturally evolved toward a state of higher entropy. This gradient, this flow from order to disorder, is what we experience as the arrow of time. We remember the past because it had lower entropy, and we cannot remember the future because its entropy has yet to unfold. But from a quote-unquote God's eye view outside the universe, if such a vantage point could mathematically exist, the universe doesn't have a beginning, a middle, or an end. It just is. It is a static, timeless block of entangled quantum information. Asking what happened, quote unquote, before the Big Bang is not just physically meaningless, it is logically incoherent. It is like asking what is north of the North Pole, or asking for the temperature of a single electron. The grammar of the question works, but the physics forbids the answer. So when we read the textbooks and look at those neat little diagrams starting from a single bright point, it completely misses the point. It treats the origin of the universe as a mechanical clock winding up. It comforts us because human beings are biologically wired to think in terms of cause and effect. We are born, we live, we die. We expect the universe to have a birth. But the physics of the universe, the breakdown of general relativity, the information erasing epoch of cosmic inflation, the fractal nature of the multiverse, and the holographic bounds of quantum mechanics all tell a story of emergent reality. The universe didn't start with a bang, it started when the very concepts of space and time crystallized out of a deeper, timeless quantum soup. And you might hear all this and think it's frustrating. You might think that theoretical physics is just failing to answer the most basic question of human existence. But I don't see it that way at all. I see it as a triumph of human logic over human intuition. Our brains evolved on the plains of Africa to throw rocks at animals and hide from predators. We were not designed to intuitively grasp quantum gravity or 11-dimensional string theory. Yet, through the sheer power of mathematical deduction, we have managed to peer past the veil of our own biology. When you realize that time itself is not a rigid stage, but a flexible, emergent property of quantum information, you realize something profoundly beautiful. We aren't just latecomers to a 13.8 billion-year-old explosion, waiting out the clock until the stars burn out. We are complex biological machines made of that exact same primordial quantum information. We are the mechanism by which the universe is able to look back at its own cosmic horizon and decipher the illusion of time. Look at this chalkboard. These equations aren't just abstract symbols. They are the source code of reality. And what they are telling us is that the mystery of our origin isn't the failure of our science. It is a profound clue to a much deeper reality. The Big Bang wasn't a moment in time. It was the moment time itself was born from the timeless mathematics of the cosmos. And figuring out exactly how that happened, how the holographic information on the boundary projected the three-dimensional reality we live in, is the greatest detective story in the history of science. We don't have all the answers yet, but the ledger is open, the equations are on the board, and we are finally learning how to read the language of the universe.